Good evening, everybody. I started talking about the future of software engineering a long time ago, and I said, what is life going to be like in 2020? And you know what? That's less than 2 years from now. When I first started, it was a lot further. And if you look at what's going on around you right now, we have this saying, the future is already here. It's just not evenly distributed. So you can just look at what's happening, and you can have a pretty good idea of where life is going. But in our industry in software engineering, things move really fast. I started with a talk I had given a couple years ago, a similar topic, and there were considerable changes that I needed to make, because even in the last 2 years, some things have changed. So I want to talk about some of the key things I think that are going to happen in software engineering that you might not learn about in the university, but you might be paying attention to. And the first one is horizontal scaling. So in 1999, Eric Raymond wrote The Cathedral and the Bazaar. How many have heard of The Cathedral and the Bazaar? Okay, so the cathedral is vertical, and when you're building with stone, that's just about as high as you can get. You're not going to get much higher. You could add a couple steeples on the towers, and that's about it. And you only have so much land, so that's almost as big as you can get. It's a very big building, especially for the 1800 time frame. Buildings got bigger and sort of surrounded churches after a while. And the bazaar is a different concept, because when you want to get big in a bazaar, you just take a little more territory and add a few more stalls. You don't have to do too much coordination, because every stall keeper has their own ideas about what to do. They run it for themselves. And Eric Raymond wrote that he was rather astonished that what he used to think had to be done like a cathedral, which is software engineering, suddenly started working as a bazaar. He was talking about Linux, which in 1999 wasn't clear where it was going, but it was becoming much more capable than he ever thought possible. He said, Linux is a great babbling bazaar of different agendas and approaches, out of which a coherent and stable system could seemingly emerge only by a succession of miracles. So we've had quite a succession of miracles, because Linux underlies pretty much anything you do when you happen to be on the internet. So the whole idea that this bazaar is just wild and untamed, as opposed to a very useful thing that you find in many, many countries, is maybe a little bit off. The bazaar is the horizontal scaling that has no limits. Back 20 years ago, so let's go back to 1998, business software at that time, this is not necessarily software in your hardware, which is the kind of software I wrote, but certainly business software was monolithic, it was huge, and it changed very slowly. I can remember reading, can you imagine a 6-month cycle time to change and do a new release? How fast is that? That was just blazingly fast in 1998. There were big ERP databases, and they were the whole integration point of all of the data of enterprise companies. Very important, and the idea was that you wanted to make sure that the ERP system covered the whole organization, all of the different back-end processes and front-end processes, and it was on a single server, even then. Why? That's an interesting question. Well, there's this CAP theorem. If you haven't heard of it, you might look it up. It basically says that if you partition your databases across multiple servers, you have to make a choice. You can either have availability, instant availability, or you can have consistency, but you can't have both. And of course, nobody wanted inconsistency. So availability was the thing, and that meant you did not partition your database across servers. Fine, good idea, until, this is Google, and this is in 2001. It had 1,300,000 web pages. It doesn't seem like a lot now, but that was a huge number back then. And the basic problem Google had is that the internet scale is way bigger than enterprise scale. So the bazaar can get much bigger than the cathedral, much bigger. So when you think about that, how do you do 1.3 billion pages, let alone more, on a single server? Well, you can get a bigger computer, right? This is Grace Hooper, a Navy commander, and she's the one that wrote the COBOL language and did all sorts of other really interesting things in software engineering. And she said, if one ox could not do the job, they didn't try to grow a bigger ox, but they used 2 oxen. When we need greater computer power, the answer is not to get a bigger computer, but to build a system of computers and operate them in parallel. A system of computers is perhaps not as easy to do as you would think, but it's the only thing that makes sense when you have 1.3 billion and you're just starting out. So your second option is to get more computers. Now, this is the 1999 hardware rack that Google was started on. And you can see it's just a whole bunch of little PCs. When they finally revealed that they didn't have a big server, they had lots of tiny little servers, and they had software that figured out which one went bad and kicked it out, it was like, what a good idea. Who would have thought of that? They really were the first one that thought of, why don't we run on a whole bunch of little things instead of one great big thing? The concept of scaling horizontally, of course, Grace Hooper had it long ago, but it didn't really become the practical thing that was underlying software until about the time that Google decided the internet was too big to have a single server. So it's scale horizontally. The concept that they published in 2003 was, their problem was to search the entire internet and return responses instantly, like sure. So what they did was they broke files into tiny little pieces, because queuing theory says lots of little pieces are faster than great big chunks. They made 3 copies approximately of each piece. They spread the pieces across many servers, and they managed the whole mess with software. It sounds messy, but believe me, it turns out to be a whole lot less messy than trying to stuff everything onto a single piece of hardware. So that concept, when it was published, seemed really remarkable, and I'll show you later how it actually started the big data movement that turned into Hadoop. But let's go to Amazon in 2001, same time frame. They are supposed to handle a gazillion transactions all at the same time, right? Sure, especially during the holiday season. So what could they do? Because it wasn't quite working. They got one great big massive computer to replace their almost massive computer, and everything slowed down. So they had to do something different. So the option is to scale vertically. And at this time, transactions are handled by the database. They get logged, they get backed out, they make sure that they're all consistent. That's the database's job, okay? That's why you need the big central front end or back end. So your option is to get a few more computers, maybe in more regions that can handle these transactions, bigger databases. Or the other option is to forget about the database handling the transactions. Instead, you want to scale horizontally. So if you have 4 things that happen during a transaction, and 2 of them are bottlenecks, well, you just, scale that way. You just add some more services that are identical to that service, so that wherever your bottleneck is, you can expand horizontally. That concept of breaking apart big chunks and then expanding them horizontally became the whole architecture of there were many, many attempts to do service-oriented architecture, but this is the one that finally eventually worked. Took Amazon from 2001 to 2006 approximately to get it figured out. So it was not simple, but once they did it, they broke their transactions into services, and they replicated the bottleneck services. And each service was owned by, famously enough, a two-pizza team. How many have heard of Amazon's two-pizza team? Okay, so I'll tell the rest of you where it came from. As about when they were having these very slow transaction services at holiday season in about 2000, every time that they got to January, the executive team would get together and say, oh, well, okay, we survived, but what are we going to do next season? Because Jeff Bezos imagined getting bigger every year, and they were not able to handle what they had. So they got all together and decided what they had was a communication problem. And they went to Jeff Bezos and says, we have to learn how to communicate better. Have you ever heard that? Yeah, right, okay. Okay, so Jeff Bezos says, wrong. We have to learn how to communicate less. Because think about it. He imagined a much bigger company than they had. And if communication was the problem today, they weren't going to solve it by getting that communication better. The only way they were going to solve it was to figure out how to have less communication. And in fact, he said he had this belief that independent agents that could make their own decisions were the only way for serious scale. If you look at the internet and the way it grew, it only started growing when you could have independent nodes on internet at all various places that could do their own thing without having central control. And so he believed that it had to be lots of separate teams. So he decreed that teams at Amazon needed to be two pizza teams, that is, teams that can be fed by no more than 2 pizzas for lunch. Right? Okay, 8, 10 people max, and that's it. And then teams had to be able to do whatever they did without having to communicate with other teams. As I said, it took them 5, 6 years to figure out how to make this work, but that's today the foundation of Amazon Web Services. I'll talk more about that in a minute, but let's go back to horizontal scaling of data that happened in the same time frame. So if you take a look at 2001, again, we're back there with Doug Cutting, and he's joined by Mike Carfella. Yeah, Mike Carfella, and they both decided that they wanted to do a web crawler, and so they had something called Lucerne, which was one of their wives' names, and they decided to put it on Apache, an open source thing, and they put their web crawler Hutch. So this could now do this cool thing of crawl the whole web and gather information. Problem, once they gathered it, they couldn't fit it on a computer. Okay, so how do we stop that? Like that. So how do you put all that stuff on a computer and organize it? They put 4 mini computers or PCs together. They had a massive amount of software to coordinate across all of the 4. It was a huge problem they couldn't figure out. But then, in 2003, Google came out with its file system paper, and I showed you 2 slides ago the structure that Google came up with, how it did its slides. And these 2 guys took a look at it and said, wow, that's cool. They took that as a spec, and they wrote a system that they put in Apache, open source, to do exactly what Google described in their file system paper. It was a really interesting idea, they decided, and that became Hadoop file service or file system. And then in 2004, Google came out with the MapReduce paper. So the MapReduce paper says, now that you've got all this junk spread across all kinds of servers, how do you really rapidly decide the answer to a search question, for example? And that's what MapReduce does. It quickly reduces stuff to different outputs from huge big data maps. I won't go into it because probably I don't understand it too well, but the concept gives you very, very rapid response to stuff that's spread across multiple servers all over the place. It's the way that Google was able to take all that data they spread out there and quickly come up with an answer to any search. So they said, okay, sounds like a good idea. They copied that Google paper too. And over the time frame from 2006 to 2012, those 2 guys were hired by Yahoo, who decided to switch to Hadoop. And the deal was, we'll only work for you if you allow us to put all the work in open source. So it all went to Apache. And during that time frame, all of the big Silicon Valley companies collaborated, talked about it over lunch, and dumped stuff into the Apache open source. And just, I can't tell you how many hundreds of thousands of engineering hours went into what eventually became Hadoop, the basis of our current big data. So after 2012, we can talk more about it, but you didn't notice that, at least until 2012. But it took all of that time growing up to become a great big data handling system. So now our database doesn't have to be on a single server anymore, and we can get at it real fast. When you think about big data systems in general, you have to think differently about software engineering. This is from Carnegie Mellon, the Software Engineering Institute at Carnegie Mellon. The people who've spent lots and lots of time studying what software engineering is all about. Sometimes I think that they're a little behind the times, but in this case, they basically say big data applications are pushing the limits of software engineering. It's essential that the body of software engineering and software architecture knowledge evolves because we have to capture this whole concept of software engineering for big data systems. When you're involved in big data, you've got an inherently distributed architecture by definition, which hasn't been an architecture up until, mid say 2010 timeframe. And you have to explicitly handle, because it's distributed, partial failures. You have to be able to deal with concurrency. You can easily have two things doing things that used to be done first this and this, but now how do you make sure that how do you deal with the fact that they all happen at the same time? Consistency. So what happened really, and especially starting with Werner Vogels at Amazon and then subsequently in all of the big data systems, is maybe eventual consistency is good enough. Maybe it's much more about fast access than precise consistency at all times. When you can do eventual consistency, you don't have to lock your databases out anymore. And I can't tell you how many locked database problems I had to deal with back before the idea was that databases don't have to be locked, okay? Eventual consistency is kind of neat when you finally realize it's actually not such a bad deal. Replication, because there's going to be a lot of it when you have your replicated services doing the same thing. And latencies. Lots of unknown types, lengths of latencies. And stuff that can just sort of all of a sudden get slow really fast. So you need a resilient architecture. You need an architecture that replicates the data to ensure that you have availability because stuff fails. I like to call the internet like building on sand. Stuff fails, guaranteed. If that's what you do software for. You do software to deal with the fact that stuff fails. Design components to be stateless. Stateless. So objects, for example, are not stateless. They actually are state. But in the internet, stateless is more important because stuff can die anytime. And if stuff can die anytime, you have to restart it. And if you restart it, what state is it in? So you have to have stuff that's idempotent. That is, you can run it again and get the same answer. Stuff has to be able to be replicated, and it has to be tolerant to failure of all the dependent services because they will all at some time fail. And you can be sure of that. So you think differently about how you deal with stuff when you're dealing with any kind of big data or actually any software that sits in the cloud. So let's go to that cloud thing. The big engineering change was the concept that infrastructure is code. You no longer really think about physical infrastructure. You think about code being the thing that deploys your infrastructure. Way down there, somewhere that you don't ever see, there is probably some hardware, but that's not what you're dealing with up at the software level. That's not really true, but it's, the way to, a metaphor. So you've heard of Conway's Law? Conway's Law? Anybody? Okay, so Conway's Law it works. I mean, it's a law that actually, it's one of those laws of physics rather than laws of Conway, which says that your organization architecture and your system architecture are going to match. You actually can't really do much about that. So learn to either match your system architecture to your organizational architecture or vice versa, because it will happen in any case. And here is an example of that. So remember those 2 pizza teams at Amazon? Okay. And so we have Jeff Bezos saying they're autonomous, they don't have to communicate. So you have these autonomous teams. What does autonomy mean? Autonomy means independent deployment. Whoa, okay, so that's interesting. Now pretend that you're an ops. And you got all these teams deploying all of the time. And you don't like that because in ops, deployment means late night calls, problems, crashes. If nobody ever deployed any software, then you wouldn't have to lose any sleep in ops. But so the problem there was there's a whole stress in operations. And Chris Pinkham, who was the vice president of infrastructure, got just a little bit annoyed at how all this stuff was messing up his people. So he said, tell you what, why don't we have a self-service deployment mechanism so that the teams that deploy software can worry about their own operational problems rather than us having to worry about it. Why don't we just let them deploy all by themselves? Kind of interesting concept. He proposed it and sent it up the value chain, and he said, the management chain, and he said, you know, maybe we could even sell this. And if you know anything about Jeff Bezos, you know that he said, sell it, that sounds cool. So it took a little while. It went all the way up and all the way down, and by that time, Pinkham has gone to South Africa, where he grew up, or he returned home, and so he got called from Amazon saying, hey, would you like to continue working for Amazon there and start up a team and do this cool thing that you were proposing? So he did, and in fact, some of the people who used to work for him in Seattle moved out to South Africa, and he hired a bunch of people there. And he led the team, and 2 years later, EC2 was done and deployed live into what became Amazon Web Services. So in 2006, it launched, and the rest is history. Today, Amazon Web Services is about a $20 billion a year business, and that same concept of basically 2 pizza teams having their own ability to decide who their customer is and what they're going to do for that customer, who their consuming services and providing services are, and making independent systems hasn't changed. The fact is, most of us in software thought they were crazy. You know, I thought they were crazy because I heard they didn't have a central database. We're talking about a big retail company selling stuff, doing, fulfillment, and no database? Help me with this. So I thought they were crazy, or they knew something I didn't know, and it turns out they knew something I didn't know, because they weren't crazy. And so there they are doing this stuff, and it took quite a while after 2006 for the rest of the world to realize that this whole concept of services, if you do it the way that Amazon did, with very hardened boundaries on the edges and specific contracts between them, turns out it works pretty darn well. Actually, a lot better than most of the stuff we used to be doing. So I'm going to propose to you there's no doubt a cloud in your future. Because economics, generally speaking, the cloud is cheaper, it's more stable, it's more secure, and it's more expandable than almost all on-premise data centers. Now, that doesn't mean that it's always that way, and it doesn't mean in every domain it's that. But generally speaking, the CIO of the US government told pretty much all the people in the government to move to the cloud because our on-premise stuff just isn't as good. And the other thing is that when you have applications that are designed for big central databases, data centers, and you try to move them to the cloud, you have to rethink your technology because they don't work so well in that cloud environment that has all those issues we talked about with big data systems, because you will be running on a bunch of sand. So when I think about the cloud, I still see a beach, and sand, and everything could crumble unless you really know what you're doing. And that's where the infrastructure as code comes in. For example, containers have been really an important concept because they give you a process to deploy for deployment that packages everything in identical kinds of containers that are handled the same way below, and you can just deal with them without worrying about all of the rest of that stuff down below. The other really big thing is what came to be called serverless. When I first heard about Lambda, which is the concept that you can call AWS and you don't have to have it put a server together for you and then run something on the server. If it's really a short call to do some really tiny little thing, they'll just do that little thing and they'll charge you just a very small amount of money and go away. And since I did software for monitoring machines, I definitely envisioned how my machines had to have somebody listening to it all the time, and having something listening to machines is a whole different game than having a machine trigger with an interrupt and have a little tiny Amazon Web Services picks up that and sends it down into some database. So serverless has become really big, and interestingly enough, it also has usually had strong cost reduction for customers. So many customers I know of said, I went to serverless and I'm saving a factor of 10 in the cost I used to pay to manage my own servers. And then there's software-defined networks. Google is especially big on these because it doesn't use network hardware anymore, because its networks are too big to be to use hardware anymore. So now we're seeing hardware coming in and being another set of infrastructure as code. So the third thing then is the new technology stack after you have your infrastructure as code. If you look at IT departments, and this would not necessarily be also the embedded software, but IT departments in 1998 kind of looked like this. There was a big, thick client-server app sitting on top, and there were some stacks. There was some operating runtime middleware, and then there was great big, as I mentioned, physical ERP database or whatever. Today, what you see instead is a thin app, maybe on a mobile phone or somewhere, and there's a whole bunch of services that are assembled by developers to which that app responds, and down at the bottom, the best available hardware that you can find is what's storing your data. So if you look at that concept, you have a whole different way of thinking about the technology stack you have to deal with. The big thing that I like to think about when I think about the technology stack is this dependency problem, because in my opinion, especially in the enterprise architecture we used to deal with in our business environments, we had like one great big dependency generator there in that layer. See the pink layer? It says data. Okay, this is our vertical cathedral, and in that cathedral we have data, and that data is where all of the important stuff about the company resides. Now, if I have an app out here and I want to change, I have to change something in the database, which means every other app that deals with that little piece or any piece of the database has to be tested. And when you think about it, that database becomes a massive dependency generator, causing huge dependencies which require lots of stuff to be tested before anything can be deployed, which really is the cause of some of those massively long releases that fortunately we're finally getting away from, but they used to be huge. So a federated architecture of any type tends to be the technology stack you see today, and certainly what you're going to see in the future. Typically based on a cloud, and you have, this is horizontal scaling, and so you have apps that have their own data, their own tech, and their own thing that they do up top, and when it gets down to the bottom, their own the kinds of applications that make the business stuff work. And it's all built on the cloud of some sort of infrastructure as code cloud. So that is what I'll call the new technology stack. The problem comes in, what are these things that own their own data and that are isolated from other things? What do they look like? Well, what they have come to look like, at least now, in this few years that we were talking about, they come to look like microservices. So a microservice is a small, useful, independently deployable service, and it's owned by a full-stack team. The team includes ops, it includes the people who are going to decide what it does, it includes the people who are going to code it, it includes anybody who's going to test it. It's basically a complete full-stack team that can make that service work. Now, oftentimes you'll find whole components that'll have a full-stack team. So we were looking at the Saab Gripen organizational structure, a big aircraft in the fighter jet in Sweden. And they have various components. Let's just take the engine, okay? The engine has a chief engineer and maybe 8 teams, and those 8 teams completely deal with everything about that engine and all of its interfaces with the rest of the system. So basically, for any component or any microservice, you have a team or a few teams, maybe 30, 50 people max, that know everything about it and are independently responsible for it. The practice with microservices is no central databases. Instead, you use APIs with contracts. The contracts will be SLA, service level agreements, and they'll be, if you give me this, I'll give you that. There's extensive automation with microservices. And the extensive automation includes automated testing. It includes automated interaction testing, and it also includes a whole bunch of monitoring while it's running, because remember, the team remains responsible for it in operations. And then the teams need to have situational awareness. They need to be sure their service is performing. They need to make sure that their consumer services get what they need, and they need to be sure that they operate correctly with the provider services. And with that, my immediate neighbors and my job kind of thing is the way that these things are managed. So it comes to, how do you deal with software engineering with APIs rather than software engineering with databases? Because that's where the cloud goes. You're working through APIs rather than through a database. In some sense, APIs are an architecture. They enable those service architectures. They lower integration friction, and they have local persistence. And in this environment, they actually replace databases. You will have a directory of APIs rather than a database to tell you what it is that's going on in a whole environment. So where there used to be that central database, there still is some central knowledge. It's just in your API directory and your API contracts. And those are the things that become sort of the hardened center of everything. But they can be changed on a one-at-a-time basis. And usually the only thing, if you change this API, is any consumers or any providers that go through that API. If I'm the provider and I can change it for my consumers, I can also hold on to the old API. So, those old guys can still do what they did, and I can make a change. So the dependencies are so much less. And you can also think of APIs as a product. Okay, so you have a responsible product team that owns the API. They have specific consumers for their API, and they evolve the capabilities of that API. So, for example, think about a thermostat. A thermostat essentially looks like an API to the rest of the world. And all of those little things that I can put in my house, almost all of them look like an API. When I deal with a skill for Amazon Echo, it's an API, really. The next thing I want to talk about in this, where we're going, is smart, physical, and resilient. So the entire software engineering today is not just about business and enterprise software, and so much not just about business and enterprise software that really the future is with smart connected products, like, their autonomous vehicle. The autonomous vehicle technically is pretty real, but from a procedural process, interaction with people, interaction with government entities, there's a lot of ways to go. But it's got some amazing stuff that's going on, and it's not just an autonomous vehicle. There's so many similar things that are being developed in many places. This is a tennis racket that's from France, where they put little sensors in it. And then they went to the Tennis Association to allow the racket to be used in competitive play. Now, apparently they don't allow the phone to be monitoring it during the competitive play, but you can get a whole dump afterwards of everything you did when you hit the ball and what the speed was, and you can use that then to improve your game. It's become a really big seller because all of a sudden you have a whole nother way for tennis players to improve the way that they do things. Or there's the Amazon Echo and the Spot, which I thought I would never use because I really do not like talking to devices at all. But turns out that I got some new lights and some plugs that are connected by internet to, through an API to the thing, and now I can tell my lights to turn on and off, and I actually think it works pretty well. And then I decided, well, I'll see how that timer works. So now when I want to do a timer when I'm cooking, I just say, Alexa, set the timer for 15 minutes, and it's easier than my hands full of cooking stuff, pushing buttons. So, and the interesting thing about this is it's got a huge amount of intelligence in there, but that intelligence is not in the edge device. It's all up in the cloud. So if internet's out, this doesn't work. So for companies like this one, you have to have intelligence in the edge device. You can't do too much in the cloud because it's oftentimes not there. So you can't count on it. Now, I can't count on it either. So if the cloud isn't there, my lights don't turn on. That's a fact. But anyway, it's interesting. And then there's whole industries that are automating things like farms. So John Deere is big in the US. They can drive autonomous tractors have been around since long before autonomous cars, by the way. They can plant fields, but they not only plant the fields, they also measure the soil in different places. They decide how much fertilizer to put in. They decide how, the depth of the seeds and how many seeds, and they just optimize that whole farm for production. Pretty interesting. Then, while they're at it, they pick up information about all the other farm devices that are around. So if you happen to be a competitor of John Deere has kind of taken over that farm information system, and then they have those nice web app to tell you when to sell your stuff and lots of stuff like that. So it's a complete farm system, and what they found was it only works, just like you guys found here at this company, it only works if you have really skilled service people available the minute a farmer has problems with his tractor. Because if his tractor goes down and he's in the field, and by the way, when you're harvesting, you're in the field almost 24 hours a day, swapping drivers, you have 15 minutes before a service person better be there, either remotely or on site, to fix that tractor, because in 20 minutes it better be back in the field. And then there's GE with its various types of predictive information so that it can predict when different pieces of your assets are in need of maintenance or are going to fail. And then just a whole area of deep learning from especially using visual pattern recognition to recognize things. So I love the story of the guy in Japan, the software engineer whose parents sold cucumbers, and they needed to sort the cucumbers because of the market. And that was the job he hated growing up as a kid. So he went online, learned how to use TensorFlow, and created a cucumber recognition system so that now they're sorted automatically. Cool. But that's amazing, really. There's so much stuff that you can do. Just, one software engineer studying TensorFlow and automating his parents' cucumber sorting changed the life for a lot of people. So there's lots of stuff going on. The other thing that's going on is this whole area of digital twins, which has to do with if I have a device there, I also have an electronic version of that device here. Maybe I can even use augmented reality to look at it. But for sure, if I'm mirroring its problems, I can start seeing things going wrong. I can possibly do that remotely. I can see when it's failing, what the problem is. I can do a whole bunch of stuff. So basically, it's a learning system, so you monitor and optimize an experiment with real, not just one piece of real equipment, but interaction of many pieces of equipment. You can have a digital twin of a whole area, a whole, say, electrical grid system or something like that. And the other thing is you can mitigate danger. You can deal much better with stuff that's remote, and you can deal a lot better with complexity. Now, this is just kind of new, like only a couple years old, but you can imagine that digital twins could become a really big deal in the future because there's so much of these things, optimizing and remoteness and complexity, that could be improved if we could figure out how to use digital twins or some virtual reality like that in order to make them better. And then there's also the augmented reality. This today is mostly used in things like helping maintenance folks decide how to maintain equipment, or helping medical teachers teach a group of students how to look at, some heart or something like that. But it's just starting. There's so much more that's going to happen with augmented reality and with digital twins and with virtual reality. So it's coming. And the last area that I wanted to talk about here, I talked about stuff is getting physical, stuff is getting smart, and it's also getting resilient, because we have all of these things that are not individually resilient, but I love this picture. It says good weather doesn't make good sailors. How many companies want everything to go perfectly? But in the end, if you look at, fire departments or emergency services, the way they learn how to deal with chaos is to inject it in an exercise. So the way that I think this was from Amazon, but Amazon and Google started this approximately the same time. They started injecting chaos into their data centers. Planned injection, but something that would take it out for a day or two or three. They call it game day. And Amazon, they call it, I forget the name at Google, but they basically effectively pull the plug or something on massive pieces of equipment and make sure that it can survive, keep track of everything that goes wrong, find out what is the problem, what's missing, where is a process that should be updated, where is all kinds of stuff like that. They figure out before the things take themselves down what is happening. So resilience engineering is getting to be really a big deal. It starts with Nicholas Taleb's book about anti-fragile, where he talks about there's fragile things, and there's robust things, and then there's anti-fragile things. So I like to think about anti-fragile things as those things that, what happens when you get a flu shot? Do you get flu shots? I'll get a flu shot. Okay, so what am I doing? I'm injecting my body with bad stuff so that it'll get hardened against disease. That's what anti-fragile is. By causing limited, contained failure, attacks on the system, you make a stronger system. That's what this is all about. This is the Simian Army from Netflix. They started out with Chaos Monkey. Chaos Monkey goes in there and does bad things, increases latency or whatever the heck, just bad failures. I heard a talk, and we were talking to one of the guys who started this, and he said, yeah, we test, but what we really need to do is test stuff that people aren't, test designs that are not going to be able to be tested by, does it do what it's supposed to do? You want to know, does it not do what it's not supposed to do? So they inject failures, and the failures will take down services. And the team owning the services then has to figure out how to take that service and fix it so that whatever that latency issue or whatever that issue was, lack of response from a call or something like that, they have to figure out how to make their service immune to that problem. They have various levels of armies. that do bad things, including that attack security and attack other things like that. And then they make sure that when stuff goes wrong, the teams fix it. And then they have the Chaos Gorilla, which what it does is it takes out a whole Amazon region, because Netflix sits on Amazon regions. And Netflix can survive a whole Amazon region going down because they practice it with their Chaos Gorilla every so often. So if you want to look at software engineering in the cloud, here's what used to be, and here's what is coming. Used to be monolithic architectures were thought to be good. We now look mostly for federated architectures. Used to be the database was the big integrator, and now we look at APIs instead as connectors. Used to be that there were stateful protocols, but we have to think really hard about not having state. There used to be consecutive execution. This follows this, follows this. But not anymore. You can't count on that. So what are you going to do about it? There used to be synchronous communication. It's sort of like getting on the phone, and I would talk to Tom on the phone. Asynchronous communication is like text messaging. So if you think about that, does everybody always see your text message? Do they always respond to it? Not really. So you have to rethink how you program from talking on the phone to doing text message. Procedural program then changes to event-driven programming. So when I did process control systems, I did a lot of event-driven programming. It was pretty natural. But I understand that people who start out with procedural programming find it hard to think that way. I find event-driven programming pretty natural, but I think of things that way. But those who didn't start out thinking about event-driven programming often have a hard time. Data warehousing, well, that was interesting once. Now we're looking more for big data, for artificial intelligence, for machine learning, and that's really going to take over what used to be data warehousing. And we used to talk about no defects, not anymore. There will be defects. Now we have to say, defects happen, and are we resilient to it? Can we recover? It's not about being perfect. If you try to be perfect, you'll waste way too much time and effort, and actually you'll be chasing the wrong thing. You need to chase recovery, not no failure. So you need to expect failure, you need to plan failure, and you need to be able to recover from failure, especially as you move into any type of infrastructure as code or cloud kind of environment. So this is our legacy from the good old enterprise software, where a lot of software engineering, at least textbook stuff, came from. And here we have the Internet of Smart Things, where we're going to have to think differently about how we think about software engineering. So now I talked about that, but I have another thing I want to talk about. So I'm going to just pop it on the back here. Okay, but this is my future of software engineering. This is a book about DevOps. Now, DevOps seems kind of weird, especially to people that are doing hardware and software, but it's the concept that those ops people and the dev people are one team and work together. They got to add a product person or a system engineer or a chief engineer or something like that. But the whole idea is, in this book, they talk about how we have to think much bigger about software than software. And the three things that they talk about, the three ways of DevOps, are flow, feedback, and experimentation and learning. So I want to talk about those three quickly here. And you start out with this. One thing we know for sure, absolutely guaranteed, is that if you have a complex system, this does not work. You cannot smash a complex system and know what's going to happen. You have no clue. It's just like whatever happens. This is our Big Bang, and Big Bangs are interesting, but they're surely not predictable. If you want predictability, this is not the way to go. Instead, for complex system, here is what actually works. Right? This whole concept of continuous flow rather than big releases has finally become, as for sure enterprise software, the standard concept. I have to say, though, that back when I did software for process control systems, we kind of thought this way anyway, so I'm not so sure that we didn't do that smash thing too often. We were maybe knew we had a complex system, I don't know. But the concept of continuous flow has to do with having a deployment pipeline that handles all of the kinds of things we used to do manually. It's like taking our tools that we as software engineers have and applying them to our problems instead of our customers' problems. Sort of like, have you ever heard about the shoemaker's children don't have any shoes? Okay? Sometimes we software folks, we software engineers don't use our own tools to solve our own problems. And this is essentially instrumenting our work so that we can not have to have a whole bunch of manual intervention. So this book came out in 2010 about continuous delivery, and the whole concept is to build a deployment pipeline. So basically you start by having by defining in an executable language what the acceptance test is going to be. Not in verbs, not in verbiage, but in executable tests that you can understand by looking at it. You have cross-functional teams that include all the different functions. You have automated build, automated test, automated database migration, automated deployment, automated all of that stuff. And you operate incrementally and deploy to a single trunk, not to branches, okay? So branches used to seem like a good idea, but in this world, if you have a branch, it doesn't live more than a few minutes. It's very short-lived. So you basically do trunk-based development, and software is always ready for production at all times, or everything stops until it is. Because in this case, everything is always good. So it's not about finding bugs. It's about not letting bugs in the first place. It's about having a good system, always under test, constantly under test. And if I add a little piece and suddenly my test don't work, guess what? It was the piece I just added. Maybe it had some unintended consequence down here, but if I have a good, stable, tested system and add a small piece, and only one piece at a time and very, very fast, I rapidly test, and whoops, doesn't work anymore. I take that out and figure out what I did wrong. That concept has taken out of software engineering a massive amount of troubleshooting and bug finding because we don't let them in the first place. And then the second one is feedback. And for that, we're talking about full stack teams. And if it's hardware, software, you don't have a hardware team and a software team, you have a team, hardware and software. Sense and Respond is an interesting book by a couple of designers talking about the job of these teams then is to not be told what to do, but to sense how things are going against high-level objectives and then respond. So, why? There's product managers, maybe whatever you want to call them, thinking, oh, if I only had these 5 more features in my code, like in my system, I could sell more stuff, or the product would be great. Well, yeah, probably 2 of them are really going to be good. Probably 3 of them aren't. And if your process says you have to know everything, then you have to pretend they're all going to be good. If your process says, we accept that nobody knows ahead of time what are the good things and what are the bad things, and we have teams that do experiments and learning to figure out what are the good things and bad things, then it's quite all right to have the product manager wrong half the time. Or perhaps in there's some references down here. In a spec, it's more like 2/3 of the features or of the requirements don't actually need to be there. In a detailed spec, so your best approach is to be lazy. Don't implement too much stuff because only 1/3 of it's going to be worth doing. So what we want to do to deal with this whole area is to move from delivery teams that are given instructions or features or something to implement and measured against do they do it, to problem-solving teams, engineering teams, by the way, that actually think about how to solve a problem, and what you're measuring against is the outcome and the impact, not the outputs or the features that are delivered. So if we look at experimentation and learning as our last thing here, you think about you're maintaining a continuous two-way conversation with the market, with the people for whom you're developing the product in some way. You have small multidisciplinary teams that include all the different functions. They understand the strategic intent of what they're supposed to achieve. They have clear metrics of what is good, and they have constraints. If there is a deadline that has to be there, they understand the deadline. But they aren't given the, we have to have exactly this and that deadline there. Here's the general goal that needs to be achieved, and here's the deadline. They have the freedom to act without permission from colleagues or from management. That's where the get rid of dependencies comes in. There's frequent, continuous deployment, whatever makes sense in your domain, to obtain feedback from the market. And then the team is focusing on learning. They're focusing on what do customers love? How do we know? They have hypotheses about what customers will love, and they try to disprove, just like a scientist. And success is meaningful outcomes. It's not proxies. You've heard of this thing called cost, schedule, scope. Ever hear of that? You know, your classic project metrics are proxies. Lots of things that might be in between a team and the customers that are using what they're developing are proxies. And every time you go through a proxy, you lose a large amount of information. And that information just is lost. Every step through a proxy is maybe 50% of the information that was in the head of the person here doesn't make it to the head of the person there. You got 2 steps, you've lost 75% of the information. That's pretty much. So I'm just going to summarize what I said, and then there'll be time for questions. So the future of software engineering, thinking about it in a cloud or some sort of cloud-like environment, has to do with scaling horizontally rather than vertically, infrastructure as code. There's a new technology stack, and think about devices as being smart. Software sits in physical things, and software systems have to be very resilient, not perfect, resilient. That's different. And then the 3 ways is flow with some sort of deployment pipeline, feedback with hopefully full stack teams, and experimentation and learning. So all of these things are happening somewhere in the world, in some areas of software and not others. But I bet you if you look hard enough, you can find, because I think the future has pretty much arrived. Thank you. The fact is that in continuous delivery, stuff is far more defect-free than in a manual testing environment, far more. It's far more defect-free than when you do a big bang and you discover 10 things are wrong and you can only find 6 of them because you don't have time for any more. So you have a much, much more robust process for delivering defect-free code. The observation that I have of anybody using continuous delivery is significant increase in quality, not decrease. So the idea that fast is bad quality is just plain wrong. I have been in the world of lean for many years. The very first thing I did was in a manufacturing plant when we moved from very slow manufacturing processes to very rapid ones. And the first thing we found out was if you didn't get the quality right, you couldn't do just in time. So flow never works unless quality is completely cared for right on the front. So continuous delivery, first and foremost, is an improvement in quality program rather than a decrease in quality. So if you think about it that way, speed and high quality go hand in hand. You can't do high speed without high quality. It doesn't work.
Thanks. That does sound really great, and this is what I heard also from one of the developers from Spotify. They said, we don't have testers. We can fix a bug and deploy it in a minute, so it's actually faster than running the regression. We deploy every week. If we have a bug, we can deploy every day. But what I see as a user, I've got updates for Windows every Tuesday. I get updates for my phone every month. With new update, 1 bug is fixed, 2 bugs introduced. As a user, I don't see
Okay, that's Windows, right?
improvement.
Are you talking about Spotify? Do you see bugs in Spotify every week?
Well, I'm not.
See, I don't know what process Microsoft uses, but I'm going to bet that it's not necessarily the continuous delivery
They
process.
moved to this software as a service. Updates gonna be, I don't know.
I
maybe not
understand they're
every
doing
Tuesday,
updates
every
fast.
day.
I understand that you're seeing defects, which means that they have not tested in their deployment pipeline the thing that you want to works. Because if they had tested it in their deployment pipeline, that software never would have gotten out. So they do not have a proper continuous delivery framework. Now, let's go to Netflix, for example. Netflix doesn't actually worry so much about specs as they worry about their chaos monkey not, once the chaos monkey finds a defect, you have to fix it, okay? So you might see defects from Netflix, but you should never see the same one twice from the same area. Because once that team finds out that this particular area of their code is causing problems, they have to fix it. So it's the kind of stuff where they never would have seen it otherwise. So I hear what you're saying, that as stuff comes at you fast, it feels like there are more defects, but I don't know the process behind that. But if they're not catching the defects behind it, then they have not automated the spec that says it should not do whatever it is that you don't want it to do. That's not in their testing pipeline. Now, if you have a test pipeline and something bad comes out the end, you should be replacing whatever caused that with a test up here so it can't come out again. If you have a really good continuous delivery pipeline, then the minute that anything wrong escapes, then you do escape defect analysis, you find the actual cause, the root cause, and you deal with it up here. Now, that only works if you have very few defects to begin with. So if you're Microsoft and you have 50 million defects, maybe continuous delivery is not got all of the specs sitting in the pipeline. So I don't think it's continuous delivery that's your problem. I think it's not having a good framework for their pipeline. Just because people do fast stuff doesn't mean that they have a good quality framework. But just because people don't do stuff fast also doesn't mean they can't have a good quality framework. It certainly can. And anybody who cares about the quality downstream will.
May I add a question there? Mm-hmm. So this example before, saying framework is good and is important. If you start with something that was being created before continuous delivery being in place, and it's considerable size, let's say it's Windows.
Like
maybe it's a bit smaller than Windows, but can you turn something that has not been done with continuous delivery in mind in the first place, if it's reasonably big, it's not something really small, into something
slowly.
that will
Okay.
work?
So the way you do that is that you recognize that if you can put a framework around your whole big code base, which you believe will catch most of the defects, some sort of massive test that'll catch most of the defects, then what you're trying to do is one piece at a time, whenever you make a change, you jump out of your monolith that has some sort of scaffolding around it to test it, and you put properly tested code out in another spot, and then you go back in. And then you do another one, and then you do another one. And over 2 or 3 years, as you change things, you will have good, clean, well-tested, well-spec'd code here. And here you're still going to have your monolith, okay? And you're still going to have a not perfect test around it. But you'll have less and less stuff here and stuff that doesn't change very often. And over in the vicinity of 3 years, most of your code, which is dynamic, will have good tests around it. So you gradually move out into a well-tested environment. Meanwhile, there's that monolith that you don't totally test all the time, as well as you could. But I have seen that done, and that's what I'm imagining is going on at Microsoft. The new stuff, hopefully, is properly tested. The old stuff, you really can't go in and change the way that it's tested because it's not architected for it.
Another question here.
Mary, great to see you in person.
Thank you.
First of all, I want to just say something to what the first question was.
Please.
The fact or to expect that updates are just going to be dealing with existing bugs is a fantasy. I think that updates are also there to bring new value
Yeah.
into the product.
Absolutely.
And you've already mentioned in your talk that there is no way we're going to provide a value with zero bugs. So, I mean, it's mathematically inherent in there that the minute you put an update, you bring in new value, and the minute you bring in new value, you bring in new bugs with them that might be there. I know you're a big fan of the cloud, and I know you're also a big fan of Taleb, as you talked about his anti-fragile book. And we are now building anti-fragile system in microservices. My problem with it is that we're delivering it into a robust and not an anti-fragile cloud. Because right now the cloud is pretty much owned by 3-4 great players. And if we look in the future, we're going to have exactly the same thing that happened with the consolidation of the banks that came together, and we got the problem of 2008. As a responsible software developer, am I going to be delivering my code to about 2 or 3 cloud providers, concentrating all the information in there, and giving them sort of like also the keys to turning on and turning off the plug as they would like to?
That's a good question. Did you want to say something, Tom? Okay. So I don't have a good answer for that, but I'm going to guess that there's going to be more than 3, because I don't see any capability of doing hardware stuff in the clouds that exist. Any, because they just don't have the security for devices. I am quite sure there will be devices for clouds for devices that are different and that are more secure. But whether or not there's going to be just a few of those, so your problem remains, I don't know. I do know that there is an attempt to make sure that there is country-specific or regional-specific data servers that comply to the local laws. But just as, I mean, there's lots of banks out there. There are not just a few big ones. And still, we had a crash. And I'm not even sure that if you have lots of clouds out there, that it's going to solve the problem of the few big ones being susceptible to a crash. So I think we have to be sensible about that. I don't have an answer.
We might be seeing a beginning of an answer if you were paying attention to what's happened with Facebook. Is that news over here too?
Yes.
Yeah, and with the new EU regulation, what is it, GDPR or something like that? The Amazons and Facebooks of the world are going to have to change a lot of their behaviors. I sort of expect that the clouds are going to become more like a utility, more like the electrical suppliers or water suppliers than big businesses. Yes, they're big, but all of the electrical suppliers in most parts of the world are 50 or 60 hertz. They're 110 or 220 volts, at least by the time it gets to your house, and you don't worry too much about that. Until they fail.
That's right,
Absolutely.
until they
fail. But
and then you have solar on your roof, right?
They're pretty reliable. It is evolving. I mean, when we look out the window of our hotel up in the valley a little bit, we see half of the buildings with solar panels. A few of them still have hot water systems on their roofs, but mostly solar panels. And that is going to change things quite a lot.
That's what we expect from the cloud also. We hope that something like that will happen.
It's entirely possible that it will. The capability for machine learning is being developed so it can be in each and every one of our phones, rather than rely on a big cloud. Endpoint computing is starting to become resurgent again, but your concern is very real, but I suspect that it's going to be resolved not just by regulation, but by evolution to be more like a utility, whether that's a centralized utility like our current electrical system, or a distributed utility like our water supply system, which is a whole bunch of independent regional things, the connection being the solar generation.
Answered? Good. Okay, next question.
Hello. You talked about continuous delivery, delivery often, delivery fast. What if you have that everything in place, you can do it, but your customers don't want it? You have a lot of customers. The one who complain your software doesn't run in XP anymore. They don't want update every month. They want the big smash every 2 years. What to do?
I always ask when I'm asked that question, what domain you're talking about. Can you tell me? What domain?
Classical desktop software, like this I'm working here, we do measurement devices and we have software to control the devices. And
Okay. So I'll take any measurement device because I'll get that. When you're developing a measurement device, you want to be deploying into some emulated or simulated environment continuously. That does not mean that that device is done or ready to be delivered, but as you're developing it, you want constant delivery into your for sure, your emulated or simulated environment. And when it's possible, into a real set of hardware or sets of hardware. So in that case, continuous delivery means making sure that, because remember, in my opinion, the main thing about continuous delivery is not so much that I get it at the end, it's that I always know my software works at all times. So I always have an end integrated mechanism which I've deployed into, which guarantees me that what I just did today was correct against what I was supposed to do. But when you have customers that don't want it, some of that is real and some of that is not real. Many customers don't want it because they have such bad experience with software. And if that's the case, we have observed that when they start getting good experience with rapid software, they're actually not particularly worried about it. So people accept some amounts of, I know you don't like Microsoft coming on down, but what about antivirus software coming down into your computer? You want it all the time because you don't want all those bad things that happened last week to come into your system. So there's always going to be constant security updates, that sort of thing. Now the question is, what should be deployed rapidly if you were sure you had the quality and you weren't going to disrupt what was going on, and what shouldn't be? And any domain, that's going to be different, but my observation is that in more and more domains, if I could really count on that stuff working, I would like it, but I can't, so I don't want it. And if that's the problem, then really solid testing, automated testing will help you a lot. If that's not the real problem, if the real problem is something else, then maybe it won't. But, I mean, if I take my mobile phone, it's sitting over there, it rang, okay, as a sort of a device, it has two modes. One mode is how fast apps get updated. And for anybody to deploy an app, you can't do continuous delivery into an app environment. It takes a week or 2 weeks to deploy a new version of an app. And that's probably not going to change. Then if you look at the operating system, it's about every 12 to 18 months, there's a new version of the operating system. And that's probably not going to change. So in that environment, there's a decision that we're going to deploy at these two cadences. But those are so much faster than the cadences we used to think about when we thought about devices. So if I were doing testing devices, I would say, your customers might be getting used to this concept of updates every 18 months and app updates every week or every month. And if that's true, over time, I'm going to bet you that they're not going to want a device that gets 2-year updates. That's just a theory. But this is the way I'm going to bet the future goes.
Okay. Meanwhile, 2 questions have arrived kind of online. The first one was, will the slides be shared? Maybe I can answer that. The whole session was taped, flashed, I guess, and will be made available as video, and I assume the slides will be made available as a PDF or
I've already
something.
given the slides to
Yeah, so
whoever is
we
going
will.
to do something.
So Patrick will take care
Yeah,
of
Patrick's
sending out
gonna
the
take care of
newsletter and
that.
all the stuff. So yes. The second one, shall we fear the cloud?
Shall
Shall we fear the cloud? Is there something we are not aware of that can cause big trouble?
Well, those are two separate questions. I guarantee you the second one, the answer is yes. Guaranteed. There's something in there that you're not aware of that can cause big trouble. No question. But I don't know any technology in my whole lifetime that ever has had that not be true. I don't care if it's cars that go fast, if it's automated vehicles, you name it, new technology brings stuff that can do bad stuff. Should you be afraid of it? I've never been afraid of technology. I think the idea is to understand and manage technology and leverage it for good and keep track of the more you know about it, the more you can keep track of those things that are going to come and hit you. But absolutely, yes, there's plenty of stuff you should be aware of, and it's going to be bad. But you're going to fix it. I mean, you've got to be on the alert for it rather than be afraid of it. If you're afraid of it, to me, that's like going and hiding your head in the sand. If you're on the alert for it, it's like being aware that there's plenty of bad things new technology can bring. We don't know what they are. But think about this. So I have grandchildren, 2 that are in college. And then I have 2 more grandchildren that are 4 years old and 7 months old. And think about what kind of technology they're going to want and accept. It's going to be very different than the technology you have now. And they're not going to care too much about things they should be worried about. They're going to care about the stuff that is good, that makes their life better and more interesting. So when I think about what the young kids today are looking for, and I think, well, better that we make sure that what they have access to is as robust as it can be, as we're alert as we can to all of the issues that it's going to cause, then we try to keep it from happening. Because I have never, ever seen anybody capable of putting a brake on a new technology and saying, nope, that can't happen. The kids always make sure that it happens anyway, so they will. Some new company somewhere will figure out how to leverage it. So it's better to deal with it than it is to hide from it.
We tend to think that things are changing quickly today. They're not. If you look at the impact of the changes in the last couple of decades and compare them to the changes that happened 100 years ago, we've got nothing on 100-year-ago changes. What happened 100 years ago? Electrification, automobiles,
Airplanes.
telephones, airplanes, in a period of 20 years.
Clean drinking water.
Clean drinking water, yeah. Before 100 years ago,
No more typhoid.
people died of typhoid. The average lifespan was, 35 years, 40 years? How many of you would be dead 100 years ago? I would have been dead twice. The impact of those changes 100 years ago in the first 20 years of the last century was huge compared to these little gizmos that we've got, that we're so proud of how profound the change is. So should we be scared of it? Well, I'll tell you, people were afraid of airplanes. They were afraid of automobiles. They were afraid of television. Do you have any idea how frantic people were about the destruction to our culture, to our mind,
yes.
that television would have?
Absolutely.
I was so scared of it, I never owned a TV in my life.
This is true.
That's true.
No, the second half is true. The first half is you weren't scared, you just didn't want to deal with it.
Yeah, so, yeah, you should be scared of it, but no more scared than stuff that is baseline what we think about as civilization. You should be much more scared about the power grid going out than the cloud going out. If our power grid goes out, what happens? 80% of us die of starvation within a month if electricity disappears. And you're afraid of the cloud?
Okay. I'll take one last question. I don't do this one. I think this was really just check-in. But they did something right, looks like. So if there is one more question, I'll take one more. Okay, last one. And afterwards, we will open the buffet with Andreas.
Hi, just one last question. When you talk about this delivery flow and all the testing you're doing in parallel to the feature itself, how would you estimate the effort you put into this maintenance of all your, let's say, pipe regarding to feature? I know you cannot
So
fill it out
every
completely.
team that I know that switched from a big batch and then test and get it working and then deploy to a continuous flow with continuous testing, even though there's a lot more software, has said they go faster, they have fewer defects, and they get a lot more done. And I will never go back to the bad old days. So it feels like a lot of work, and it is a lot of work, but the alternative way that we used to do things, spending 30, 40, 50% of our release cycles finding bugs and fixing them, was pretty awful. And when you get out of that, large amounts of back-end testing and finding defects because they don't get in there in the first place, stuff just gets done better, higher quality, and faster. So there is probably a learning curve hump to get over, and probably, especially if you start with a legacy database, what do I do with that kind of thing to get over? But if you would compare two completely identical systems, one with the old manual testing and one with the new automated testing, rapid delivery, continuous integration, this one would be more efficient, higher quality, get more done. Only when they're both working. Okay, there's the transition period. But when they're both working, the continuous delivery way of working is definitely, from everybody I've ever talked to, it's preferred once it's working. With what?
They changed to this
They did.
hosting and they increased productivity 20%.
Who was that?
Salesforce.com.
Salesforce. Yeah, I can see that. Because the amount of time you spend dealing with stuff, I mean, this is a pretty classic lean concept in manufacturing. If you don't put defects in, you don't have to find them later. You don't have bad stuff that gathers defects in. Pretty classic. Well, it's just the same. If you don't put defects in, you don't have to find them. They don't get buried. You don't have to categorize and say, this is a critical defect and this one we can live with. And you don't have to do all that stuff because you don't let it happen. So stuff moves faster. And it's better. It's better, but you have a lot of work to get there. And I'd say easily a year of pain. And it's very hard work, but it's no harder than any other engineering challenge we take up and live with all the time.
Okay.
Thank you.